Hi everybody, I'm Lee and I'm here to talk about TCP Windows being demystified. And I love tech, I love talking about all of these things. This is what I'm studying and researching at university, and I want to talk a little bit about something that's been requested a few times. If I had a nickel for every time I'd been asked about it, I'd be a millionaire. But, I want to talk about how data is sent or transmitted and how data is consumed in different applications. So what I've got is a bit of a discussion around what the receive window is, what a congestion window is, what a full window is, and some demonstration. I've got some packets to go through as well, and what a zero window is and what that means and what you could look out for when that happens. So what we're going to do at the end of this is you're going to be able to identify where the receive window is, where the congestion window is, and if you can see it, how to tell the difference between a zero window and a full window and what that actually means, and some edge cases. So, receive windows, they've always been there. They've been in TCP RFC 793 from way back in September of 1981, and they demonstrate, or they determine rather, how much outstanding data can be on the wire and how much the receiver can process, and it's used for flow control. So originally we didn't have a congestion window. We could just blast data. As long as it was less than the receive window, it could be unacknowledged on the wire at any point in time. Now, as obviously latency and bandwidth increases, it can get big really, really fast. So that requirement for having outstanding data on the wire just gets bigger and bigger as bandwidth increases, and as geostationary satellites, and low Earth orbit, medium Earth orbit, and cellular connections as well, have that latency. We're going to need to have that window scaling right up. Now, originally, this was 64 KB of data. It was just a static field in the TCP header. And what we see here is I've actually got in that screenshot there an example of where the actual window is 83, but the calculated window size is 42,496, and we have a scaling factor, and that scaling factor allows us to determine or scale beyond that 64 kilobytes of outstanding data on the wire. And it's absolutely aligned to the receive buffer. So when you're configuring a socket, or you can use the system default obviously as well, but when you create a socket to transmit or receive data, you can actually specify how much that receive buffer is and how much the send buffer is, and then that'll then influence the maximum available size for that window size. So I tend to correlate the two as being very, very much related and dependent on each other. They are the recommendations when you look in documentation is typically you want it to set the TCP receive buffer as twice the size of your estimated windows, because your receive buffer determines the maximum size of the window. So small values in the receive buffer will limit the performance of an application in high latency situations, as you can imagine. What I've got here is a TCP. This is actually a screenshot taken from some of the packets that I'm going to show you shortly, showing the TCP window being completely full. It's you can see that it's not actually a field, it's expert information, and this is because Wireshark will calculate the receive window when it's or calculate how much data is outstanding on the wire and how that aligns to the receiver's TCP window. And I'll show you how you can look at that, and also show you where we calculate what the scaling factor is, and all of that stuff I'll take you through in the packets. So assuming that the server is and the application is actually healthy, reading the data from the socket, the receive window will stay high. If the application is not receiving or reading the data from the receive buffer, the receive window will drop to 0, and that's that zero window situation. So in here we've got actually an explicit, I haven't got it in the screenshot here, but the expert info is saying that we have a zero window segment occurring. The window size has dropped down to 0, and that is because typically there's some sort of resource contention on a server or application, and the application is not reading data from the socket. And I've written a couple of demo applications to explain or show that particular behavior, poorly written by me. The other window that we have in place, so we've only been talking about the congestion window, which is all about flow control, is the congestion window, which is all about the network and the network stack on the endpoints, because we've got to remember that, you know, the endpoints themselves actually participate in the network. If there's a problem with resources on a server, its network stack is going to be underperforming. You might see some issues resulting from that as well, and that's where we might see your retransmissions, for example, or excessive retransmissions, because the network stack at either end is having some problems. Slow start is the first phase that we typically see, and it ramps up quickly despite the name, slow start. Ramps up very quickly to show the available bandwidth between the endpoints. So it's going to ramp up exponentially to say, okay, this is the available bandwidth that I have, and then it's going to switch into what we call the congestion avoidance phase, where it's going to, every round trip, it's going to add one maximum segment size value, and I'll show you what that is in a minute. To the, you know, amount of bandwidth that could be, or rather the amount of outstanding data that the congestion window can send. The maximum amount of outstanding data on the wire is going to be the lower of either the congestion window or the receive window, because, you know, the receive window all about the host, congestion window all about the network congestion. In order for congestion avoidance to work, it's going to keep ramping up the congestion window until it reaches congestion, and that by that very nature is going to see retransmissions occurring, you know, as bandwidth is or isn't available. So, you know, one of the things that I would experience frequently with customers is I'm seeing retransmissions, you know, and well, that's a good thing, because that means that the collision avoidance phase and the, you know, slow start is actually working. Retransmissions become a problem if the packet is actually disappearing. And, you know, excessively at that. This is a, you know, complex topic, and I could go into this and spend an hour on this topic alone. But you will see retransmissions if they're excessive and interfering with the throughput of an application. That's a different problem. I've got here an example of the bytes in flight and the number of TCP errors that are occurring here. So you can see, actually, I used TCP Reno on this particular example, and you can see that at the start of the communication we ramp up really quickly, we pause for a second, and then we keep going up. And you can see that black line coming up indicates TCP errors, in this case retransmissions. You can see that the bytes in flight, which is a measure of effectively the congestion window, you can see drops down by about half, which is what we see for TCP Reno. It then ramps up again and then drops down. You can see at about 15 seconds we actually see a really solid congestion avoidance phase where the bandwidth slowly ramps back up again over time. So what I'm going to do now is bring up a quick demo. So I'll just jump out of my PowerPoint app, and I'm going to show you the code that I have for my two applications here. So I have a TCP client, really simple, runs as a daemon. You can ignore that code there, but effectively what happens is the application starts. I've got a few parameters here to be able to say, do I want to add delay and all that kind of stuff in here? Do I want to do quick ACK or change the receive buffer? And this is effectively how I'm manipulating the behavior of the application. So I'm actually on the server side at the moment, not the client side. So the application starts. We've got a initialization up here. Oh, where's that initialization gone? We've got an init here, which then goes and says things like effectively setting some global variables here and changing some socket options down here. Where we iterate, we actually go through the start phase. We open up the socket. And we've got here a read loop on, while we're running as a daemon. I'm going to run a select against a set of file descriptors. And if a file descriptor is readable, then what I'll do is I'll send that off to a new thread to handle. Typically this would be like a group of worker threads, but I've made this fairly simple. For every new connection I see, I start a new thread. This is obviously not something you would run in production because you could exhaust the number of file descriptors really quickly and crash your system with this. But for the purposes of this test, it made a lot of sense for me to quickly just fire up a thread. Inside the thread, which is this handle connection here, I've got the ability to go, well, while this is not closed, read from the buffer 1 byte. Again, that's terrible coding, but for the purposes of this, makes sense. And then I've got some exceptions down here, and effectively it will run through and run some commands if I want to echo data back or not. That's effectively what this TCP server is doing, and I'll put this on GitHub eventually and link it in the description below. I've got here my TCP client. The client is pretty simple. It's just using Python fire or pip fire, and it does some things like send a large echo, or send a no echo command to the server and push it to the full size of the packets I have available here, which is 14 bytes in an individual packet. Part of the reason why I've done that is I've been doing some testing with some Nagel and delayed ACK testing, and wanted to really craft some really interesting packets. But in this case, what I'm going to do is set the number of iterations and fire that towards the TCP server that I have here. If I bring up the actual packets themselves, my code actually dumps all of this out into a folder for me. And what I have here is I'm going to look at the first one here, which is the receive window. What I've done is I've statically set the latency to 2 by 50 milliseconds, and I've set the receive buffer to 32,768 bytes, and it's dumped this into a packet for me. So if I scroll down, I find my TCP communications really, really quickly. I've got here my three-way handshake, my SYN, SYNAC, ACK, and you can see here that the latency is about 116 milliseconds. And you can see that actually if we go down here into the sequence and ACK analysis, you'll actually see the IRTT, or the initial round trip time, is 1,116 milliseconds. If I go into the SYN, some important things that I see here is the maximum segment size for this network is 1,460 bytes, and I've done some maths on that to work out that I have 20 bytes for the header, or rather we've got the command I can add up to another 1,414 bytes in there. So your maximum segment size here, that's the amount of payload data minus TCP options, because they count as payload, that you can have in a single segment that goes across. Now, in this case, I've got 1,460. I also have my Windows scale here, and you saw in the screenshot earlier that it was using 512. Now, if I miss this three-way handshake, because this is actually calculated the reverse as well, we see here that the Windows scale for this one is a multiplier of 1. Maximum segment size is 1,460. If I miss this three-way handshake, there's no way for me to tell what the calculated Windows size is, and Wireshark has no way to tell. However, there is actually a setting that you can go into preferences for. If I bring up my TCP preferences, go down to TCP, you can actually set a scaling factor for assumptions if you miss the three-way handshake. In this case, I might be able to say that, well, I assume that it's multiplied by 512. Or multiplied by 1 in the case of the other one. So I'll just bring this back up again. So expanding that out so you all can see it a little bit better, I've got my three-way handshake. And what I've got here is my initial sending of data here. And I've got here the initial segments going out, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 packets, which is what we would expect from a initial congestion window size of 10 outstanding maximum segments, which is the maximum value that you can set on Linux. And you see here, after that, I'm going to wait for a round trip to acknowledge all of that data that's coming through. And what we see is that as soon as I get that acknowledgement, I'm able to start sending data again. So I still have 13,032 bytes outstanding on the wire, because this acknowledgement is only acknowledging the first 1,449 bytes on the wire. So that is up to this one here. If you go to here, you can see that the next sequence number is 1,449. which is what that acknowledgement number is down here. So I'm going to continue sending on here, which is another 1,448 bytes plus the 12 bytes of options that I have here, adding up to 1,460. And I'm going to send the next one, and the next one, and the next one until I hit, until I see the next ACK here, which is acknowledging up to 1,481. Which is that one there, I think. Anyway, moving on. I then send some more data. I get a bunch more acknowledgements coming back. I'm still following this bytes in flight here. And I can see that the receive window on the sender, you can see, sorry, the receiver rather, is still at calculated window size of 30,408. We keep going through. The bytes in flight keeps increasing over time. So that maximum value of bytes in flight keeps increasing until it hits that value of 30,408 bytes. And this is where we see that first zero window. Sorry, not zero window, rather window full event. You can see that here. There's no explicit marking in the packet that says we've hit that value. It's all expert information that's been calculated by Wireshark. And you see that here. So as soon as I get another ACK, which is about 58 milliseconds later, we actually see that I can start to transmit straight away again, but I'm only able to transmit one maximum segment size, that which is that frame here, which is that 1,448 bytes of data plus 12 bytes of options before the window becomes completely full again. We see a couple of acknowledgements come back. I can start to send data again, and again we hit window full almost immediately again there. So those two ACKs here allow me to send another two full segment sizes of data, and we see this pattern repeating over and over again as the acknowledgements come back. We end up with a window full. Now what I'm going to do is bring up the statistics. So I'm going to start with a Stevens graph because I think this looks very, very cool. You see this pattern of this staircase pattern occurring, and this is indicative of some kind of flow control problem or a congestion problem, or a congestion window problem. Typically with rate pacing it looks more diagonal if it was a congestion problem, but in this case we've got this staircase effect because we've effectively transmitted the maximum amount of data that we can. We now have to wait for an acknowledgement to come back before we fire more, wait, fire more, wait, fire more, and the process goes on. If I switch this over to a window scaling graph, what this looks like here is we're constantly butting up against this blue line here, is butting up against the green line here, which is the available receive window. If I add in the bytes in flight again, you can see that it's not like anything's crashing down to zero. It's just that I'm constantly butting against this value here until the test stops. What I'm going to do now is bring up a zero window to contrast that against. So in this case here, what I've done is I've severely disabled the server, simulating a problem with resources on that server. And you can see here that, again, just looking at that, there's nothing really all that different here in the SYN packet. We still have our options, we still have, SAC permitted maximum segment size and window scaling option as well. We get the same thing coming back here. In this case, you can see that the window size is much larger than in the previous one. I had it set to 32,768, which added to about 30,208 bytes of available window size. We ramp up fairly quickly again with our 10 packets, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We wait for that to come back, and then we see a couple of dupacks here, so indicating that we lost a packet. That's okay. We keep going on. Now we ramp up a little bit further, so beyond the 14,480, we keep increasing that as time goes on. So we're now into 20,000 outstanding bytes on the wire, 24,000, 26,000, 27,000, and then we get to about here where we start to notice some problems. We see a window full. Okay, that's interesting. But what's interesting here is that this row here, this number of this calculated window sizes is dropping, and I'll show it in a graph in a second. And so we see that we're butting against the window full again, but actually the what's happening is that window is dropping down to 0. So it's saying, stop, I can't process anymore. My window is completely, sorry, my receive buffer is completely full. I don't have any space left in my receive buffer for any window. So I'm dropping the window down to 0. And that means that the application is not reading from the socket as fast as we're transmitting data. And the result of that is the application saying, my window is full, don't send me any more data. Now, if I bring that up as a graph, I'm going to show this first as a Stevens graph. You can see that same pattern, that staircase pattern. But what looks super interesting here is when I switch it to a window scaling diagram, you can see if I take out the bytes in flight, you can see that window starts off fairly high and then drops down to 0. And that's telling me that, and it's staying at 0. That's telling me that the receiver has said, no more data, I can't receive it, I can't read it, I can't process it, don't send me anything. And I'll highlight the bytes out. The bytes start out climbing as the slow start begins. However, really quickly we run into that dropping down to 0, that receive window dropping down to 0, and that's that 0 window. So unlike where we had the window full condition by itself before, where we were constantly butting up against the top, the receive window stayed high, indicating that that's just a problem with flow control. This is a problem with the application itself, and it could be, or the server. It could be that there's no CPU cycles available. It could be that it's hitting CPU denied in a virtualized environment where it just doesn't get access to the CPUs as quickly as it needs to. It could be that the application is just written really poorly. In the case of this one, that's what I've done here. But when you're seeing 0 windows, that is a problem with the endpoints in play. It has nothing to do with the network at all. And I see this constantly. Now, there is one exception to this, and I want to go through some edge cases quickly. I'm happy to share out these PCAPs if anybody wants them. Comment, request, I'm happy to explain it or go into more detail as needed. So I'll bring up Keynote again. We'll play from here. The edge cases are really around TCP proxies and load balancers. The difference with that is that the application's actually more the load balancer itself. And in the case of TCP proxies and load balancers, what will end up happening is that because they're forwarding on data, the send buffer now comes into play before it goes on to a third-party endpoint. And if that third-party endpoint becomes unavailable, what ends up happening is that even though you've got 2 separate TCP connections on each side of a load balancer or a TCP proxy, the send buffer going to the real server or the client behind the load balancer will fill up because it can't send that data on because it's hit a window full condition itself, and therefore it starts to back up onto the receive buffer on the other side because it can no longer on-queue data onto the send buffer. And you end up in the situation where you see a 0 window going to the originating sender. So you can see that on both sides of a load balancer or both sides of a TCP proxy. But if you're looking at TCP proxies and those are the things that you're looking at, just keep in mind that that 0 window may actually be just because they can't reach the endpoint on the other side. So any questions, please like, subscribe, share, post comments down below. Let me know what you thought of this, what I can do to improve, what you'd like to see next. I've got some requests for Nagel. I've also got some requests for demystifying where the application layer comes into play in terms of reading the socket. And I'll use that demo app I had up earlier just to explain that in a little bit more detail. But I'd love to hear more questions, more topics, more deep dives. I'd be really interested to hear from. Lastly, thanks everybody for spending time with me, spending the last 20-30 minutes with me, going through what a zero window is, what a window full is, what the congestion window is, and what the receive window is. If you'd like me to go into more detail around the send and receive buffers, that layer below TCP, I'd love to talk to that as well, about that as well. So on that note, I'm going to leave you all to it. Thank you very much and have a great day.